Yo guys, welcome back to another video. So here we'll be going through the complete walkthrough of the Wednesday 5th of June 2019 paper, and this is in particular the paper 1 pure maths 1 and for the A-level syllabus. And this paper is out of 100, so we're going to try and get 100 marks, okay? Not always guaranteed, but hopefully we get what we get. Now, I'm going to show you guys how to do everything step by step, and if you guys want, you can always pause the video, try it first, and then see if your answers match up with mine, or if my answers match up with you if I'm doing it wrong. But other than that, guys, let's go straight in. So fx equals a cubic equation, guys, and you also got a couple a terms stuck in there. Now, given that x plus 3 is a factor of fx, find the value of the constant a. Alright, so first thing, if something is a factor, all that literally means, guys, is that if you plug in the root of this factor, and to find the root, you just set x plus 3 to 0, and then you can realize that if you make x a subject, you'll get negative 3. So this is essentially telling us, replace x with minus 3, so let's say f minus 3, and this whole equation equals 0. And then you can solve for a, once you replace all the x values with minus 3. So it looks a bit like this, guys, yeah? So if I set minus 3 right now to every single x, and just wrap them up nicely in a bracket, so replace all your x term, guys, with a bracket minus 3, just like this, then what I would do, I would essentially put all of these terms in the calculator. So let's just evaluate this, 2 times this in the calculator, and this in the calculator. And if you do that, guys, you get something like that. All of this becomes minus 81. The second term becomes 18 times a, which is 18a, plus 12, and then plus 5a. And we're basically done here, guys. Now all you do is collect like terms. So minus 81 plus 12 is minus 69. And adding up the two a terms, you get this, 23a. Now lastly, make a the subject, guys. All you do is add 69, divide by 23, and you got a equals 3. And we're done. So figure 1 shows a plot of parts of a curve with equation y equals cos x. So here's your cos x graph, where x is measured in radians. So diagram 1 on the opposite page is a copy of figure 1. So just quickly go in there. Alright, we can see it's another cos x graph, so literally the same thing. A. Use diagram 1 to show why this equation here, which equals 0, has only a single real root, given the reason for your answer. Okay, so there's a little trick to this question here. You essentially are only given cos x. Now, when you write something like this, the good thing is you can actually make this equation equal to cos x, yeah? So let's do it right now. If we do that, we'll have cos x equals, and to move both of this to the other side, you need to add them across. So you're going to have a plus 2x plus half. Now, the nice trick is, when you're solving for equations, if you make them equal each other, then you kind of think of these as two separate equations. Like one equation which is y equals cos x, which is already drawn, by the way, and the second equation being y equals 2x plus half. Now, when we plot this line, I'm not sure if you have to make it accurate or not, but just looking at this graph for a second, yeah, you can kind of see that this cos graph kind of ends like randomly over here. It doesn't actually end perfectly on the line. Now, because it's in radians, we should know the fact that, well, this goes up to 360, right? So 360 degrees is actually equal to 2 pi. And 2 pi is about 2 times 3.14, so about 6.28-ish, like something like that. So we can kind of think of each of these squares as, I think, 1 unit, right? Because you've got 1, 2, 3, 4, 5, 6. Yeah, so like 6.2, perfect. So if you want to plot this graph, we can say, I don't know, let's just pick 2 coordinates here. Let's say when x equals 0, so let's do it here. So when x equals 0, for this y equation, we would have y equals 0 plus half. So that means y would equal half. So that's one coordinate we can plot. So x equals 0, y equals half. Let's put that about here. Another way you can do, I don't know, let's say when x equals 1, that means y would equal, in this case, 2 times 1 is 2, plus half is 2.5. So let's just say 2.5. So the next coordinate would be here. It would be 1 across and 2.5 up, so around here. And that's it. And then we just draw a nice straight line. So the straight line should be something like that. Okay? In your case, like, always use a ruler. And now, because it crosses over here, because it intersects at this point, this is literally the real root. And we are done, guys. That's what we have to say. You could say that these two intersect at this point, indicating it's a real root. And that's it. Now for the second part here, it says given that the root of the equation is alpha. Okay, so this is literally your root. So this value is alpha. So you can kind of see like it's less than 1, right? Okay, I'm assuming it's the same question. Use a small angle approximation for cos x to estimate the value of alpha to 3 decimal places. Alright. So the small angle approximation is literally this. This means that when we estimate cos x, this is roughly equal to 1 minus x squared over 2. And this only works when x is like really small, like 0.01 or 0.2. When it's really big, then it's not really accurate. So this is kind of what they mean. Now, all you have to do, guys, now that you know that cos x equals this, just replace this cos x and, well, solve the equation. So far, this means that we're going to now have 1 minus x squared over 2, take away 2x, take away half equals 0. And over here, we have kind of a quadratic looking equation, yeah? So what I will do, I'll clear the fraction. So I'll multiply 2 across, because I don't like looking at fractions. And if I do that, I'm going to get 2 minus x squared minus 4x minus 1 equals 0. And then just clear like terms. You've got 2 take away 1 is just plus 1. And I'm going to put that afterwards, yeah? So we're going to have minus x squared minus 4x plus 1 equals 0. And yeah, guys, we literally have a quadratic equation here. Now, if you want to solve this, just use a quadratic formula. And a quadratic formula looks like this. It's x equals, minus b plus minus the square root of b squared minus 4ac all over 2a. And a, b, and c, guys, are the values in front of the x squared, the x, and the plus 1. So you can say that a equals, well, minus 1 because it's literally minus 1x squared. B is minus 4, it's in front of the x. And c is the plus 1, the constant. Okay. And if you substitute all these values back in, you should get an x value of 0.236. And this is the positive answer. You also get a negative solution, but you can drop that. Alright, number 3. So show that dy of dx, so in other words, when you differentiate this equation above, you should get this kind of form, where a and n are constants to be found. Okay, so easy way to do this, guys. When you got something divided by another thing, we can use something known as the quotient rule, yeah? It looks a bit like this, yeah? So for the quotient rule, we just let the top half equal u, the bottom half equal v, and then we just do some kind of differentiation on that. So we could just say, okay, let u equal 5x squared plus 10x. Therefore, when you differentiate this, you should just get what? 10x plus 10. Okay, so that part is easy. You just drop the power and get rid of this x. Now for v, we do the same thing. We say, okay, v equals x plus 1 squared. And to differentiate this one, it's actually not too bad. We use something called the chain rule. And the chain rule tells us that first we need to drop the power down, so we've got 2. Copy the expression, so it'll be x plus 1. Reduce the power, so it'll be power 1, so it's like that. Then you differentiate it inside. Well, the derivative of x plus 1 is just 1. So you times that by 1. And well, if you times by 1, well, you get the same thing. So you just leave it like that. So to apply the quotient rule, we just draw some arrows, yeah? And this is my method. I always say, okay, let v times u prime minus u times v prime over v squared, okay? And in words, this is just dy over dx equals, well, v times u prime, so it'd be x plus 1 squared times 10x plus 10 minus, and then you subtract against the u versus v prime. So it'd be 5x squared. So actually, let's copy this one first. It'd be 2x plus 1 times 5x squared plus 10x. Okay? And all of this over the v squared, which is x plus 1 squared. So if you're squaring this one, it'd be power 4. So moving to the next page, we just need to go ahead and simplify the top line, okay? So let's have a look. You got 10x plus 10. We could factorize the 10 out there. So let's do that now. We're now going to have, well, if you take out 10, you're going to have 10 bracket. You can copy out this one first, x plus 1 squared. And because we factorized 10 out of here, we should get x plus 1. And likewise, guys, for the second part, you can actually factorize a 5x out of this. So it'll be 5x times 2, so it'll give us minus 10x. Copy the first bracket. And because we took out 5x from here, we actually just left with x plus 2. Okay, so almost done. And oh yeah, all of this over x plus 1 to the power of 4. Now what I would personally do next, guys, I'll probably try and factorize more things, yeah? So looking at both these terms, we have a 10 and an x plus 1, and we have a 10 and an x plus 1. So let's factorize that out. So you're going to have something like 10 x plus 1, all of this factored out. And what I would do here is draw like one big square bracket and write what we didn't factor out. So we didn't factor out x plus 1 squared. And on the right side, we didn't factor out the x and x plus 2. So it'd be minus x, x plus 2. And copy out the bottom again. So it'd be x plus 1 to the power of 4. Now, conveniently, if we look up and down, we can cancel down x plus 1 on both. So cancel this one, and this becomes a power 3. Okay. We can also expand and simplify the inside. So we can have it now 10 times. So expanding this one out, if you open this bracket, you're going to have x squared plus 2x plus 1. So x squared plus 2x plus 1. And then if we expand the right side, we're going to have x squared plus 2x. And because we've got minus sign, it'll be the negative versions. It'll be minus x squared minus 2x. And all of this over x plus 1 to the power 3. And again, looking inside the bracket, we can cancel more terms out. We can cancel x squared with minus x squared. We can also cancel 2x with minus 2x. So you're just left with 10 times 1, which is 10. So your final answer, guys, for part A would be 10 over x plus 1 to the power 3. And boy, that was kind of long, but that's it. Now, next one. Hence, deduce the range of values for x for which the derivative, so the answer we just found, is less than 0. So I'm just going to continue from A. I'm just going to call this B straight away. So we want to solve this one when it's less than 0. So what kind of values x can this take? Well, just looking at the equation on the left, guys, yeah, we can just ask ourselves. We got a positive number over some kind of quantity, right? The only time this can be negative is that if the quantity itself was negative, right? So let's go ahead and just rewrite this in a different way. Let's say let x plus 1 to the power 3 be negative, so less than 0. What could x be? Well, solving this, we can cube root both sides, right? If you cube root both sides, well, you just be left with x plus 1, and the cube root of 0 is 0. And from here, you can just subtract 1 across. That means our x value is going to be less than negative 1. And that's it, guys. This is literally all you got to do. And this is the values of x, which make it negative. Okay, number 4. So find the first 3 terms in ascending powers of x of the following binomial expansion. And we got to give each coefficient in its simplest form. Okay, so to do this, we need to firstly rewrite this in indice form. Yeah, so basically as a bracket to the power of something. Well, if you've got a square root, we know the power should definitely be a half. And if we've got 1 over something, then it's going to be a negative half, so it'll be negative power. In other words, this whole thing would literally just be rewritten as 4 minus x to a negative half. Okay. Now, to convert something to binomial expansion, if the power is in a whole number, so if this isn't like 1 or 2 or 3, then we go use a particular form, guys, yeah? And the particular form tells us that we need to have a 1 inside, so like a 1 plus or minus something. So in other words, we need to get the 4 outside. And to do that, we need to factor it out. Now, the easy way to do this is to literally just divide 4. And if you take 4 out, you're just going to take the power with you. So it's kind of like something like 4 to the negative half. So you take it out with you and its power. Then you're left with 1 minus. And because you took the 4 out of the x, you'll be left with x over 4. Okay? To the power of negative half. And this makes sense in its own kind of way. Now, all we got to do now is literally deal with this and use the binomial expansion form. You need to think of the 1 plus a, so capital A, to power n. Okay, and this is the form I'm going to use here. And oh yeah, 4 to the negative half, guys, is actually the same as 1 over 2. Okay, so it'll be 1 over 2 times all this expansion, so it'll be half times that. Now, using the binomial expansion, I'll show you guys a formula. It looks like this. So just looking at everything here, we got our first term, because they want the first 3 terms, second term, and even third term. Now, what I'll do is just replace every value, and just remember, according to the formula, guys, yeah, our power n is actually minus half, so n equals, in this case, I'll write it as minus 0.5, and our a term is going to be minus x over 4, okay? So updating all the values here, you're going to see that we have 1 plus minus 0.5 minus x over 4 in place of a, and for n is the same. For n minus 1 is going to be minus 0.5, take away 1, which is minus 1.5, so that's okay. And it'll be minus x over 4 squared. And we are done, guys. All you gotta do is literally multiply this out. Now, quick trick. If you're gonna put this in your calculator, guys, like for example, let's rewrite this first term, right? In the calculator, you know you don't have an x button. So what we do, we write on the right, I'll write over here, we write minus 0.5 over 1 factorial. There's a factorial button. It looks like an exclamation mark. And then next to it, we put a big bracket. And just imagine you're going to ignore the x. So let's just write 1. Always write 1 in place of x. It'll be minus 1 over 4 to the power of 1. We will repeat this for the second one as well. If you put this in the calculator exactly, you should get 1 over 8. And then you can stick the x in front. Likewise, if you do the second part, copying exactly as it is, replace x with 1 and then put this bracket squared, you'll get 3 over 128. And because you got x squared, you stick it in front. 1 is as it is. And finally, guys, just literally times the whole thing by half to just smack it out. You should get the final result of half plus 1 over 16x plus 3 over 256. And that's it, guys. We're done for A. So moving on to part B. Now, the expansion can be used to find an approximation root 2. So it's talking about our little expansion right here. Possible values of x that could be substituted into this expansion of the following, yeah? So we got x equals minus 14, because if you replace this x minus 14, it will look like root 18, and it becomes like that. If you plug in 2, you're going to get root 2 over 2, and if you plug in negative half, well, you end up with a number like that. Without evaluating your expansion, but I personally recommend you guys kind of do in your mind, state, given a reason, which of the three values of x should not be used. Okay, so out of these three, the ones that should not be used is actually anything where the x value is greater than 4. Okay, because for this kind of expansion, and I'll explain why. If you plug in a massive value, say bigger than 4, or in this case minus 14, what's going to happen is that you're going to somehow have a really negative result. Okay, because it starts slow here, but you can test it. If you plug like minus 14 now, you get like minus 0.4 something something. So that's quite bad. If you plug in one of these two results, well, it's going to be quite stable because it's within the limit of 4. So we can go ahead and say, well, we wouldn't put x equals negative 14. Why? Because we need to make sure that the absolute value of whatever we choose has to be less than 4. Okay, and this is kind of a legit argument. Now for the second part, it says state, given a reason, which of the three values of x would lead to the most accurate approximation of root 2. Well, the best approximation now, and just looking over here, is to basically minimize the x value. Yeah? You want to get as small as possible, like not 0, but like at least like close to it, right? And out of these three choices, it's going to be this one. Typically, you'd think it's this one because it's just half of root 2, and this is a third of it. But in terms of expansions, when you plug in a small negative fraction or small fraction in general, it will become close to the answer, at least for the beginning. But yeah, and that's it. This pretty much ends the question. So yeah, we can just say x equals negative half because it's the smallest value. And that's really it. So in question 5a, it says write fx in the form of a times x plus b squared plus c, where each of these letters are integers to be found. Okay, and you also got parts b and c. Now let's just focus on part a for a second. Now to rewrite this function in this form, we first have to notice that this form is known as completing the square. Yeah. So let's go ahead and underline the function. Now the objective to completing the square is that we always need to firstly rewrite this in just x squared form. So we gotta get rid of that 2. And to kind of get rid of 2, we need to factor it out. So look a bit like that. If you factorize 2 out, you just divide 2 across. So you got x squared plus 2x plus, well, half of 9 is 4.5. And now to officially complete the square, the key idea is to underline these two terms, x squared and 2x, and then half this coefficient of 2 here, and then wrap it in a bracket. So it looks a bit like that. You got x plus 1 squared wrapped in a bracket, then you copy next term, then you subtract the thing you squared by, well, squared. So it'd be minus 1 squared. And we're pretty much like done here, guys. So all you have to do now is, instead of multiplying this out like completely, because notice how they got a little a outside x plus b, they literally stuck this 2 on this bracket, but then they left the next part as one whole number. So what we can do here is literally partition this. You got 2 of that and 2 of the next set of terms, and then you just say, okay, what is 2 times all of this? So just smash this in your calculator, guys, and you should get a 7 for that one, and therefore your final solution is going to be this, where A, B, and C have been found. And that's it, like nothing to it. Now moving on to part B, yeah, so we're going to shift this up there. It says sketch the curve of equation y equals fx. Alright, so sketching. Sketching is kind of easy, like, so depending on what you're trying to find. Showing any points of intersection with the coordinate axes and the coordinates of any turning point. Now one key thing, guys, yeah, is that when you got an equation like this, the turning point is actually found from here. The turning point in this case would be like when this part equals 0. So in other words, x needs to be minus 1. And if x is minus 1, because it's all 0, you're left with a 7. But let's do it step by step. So we say, alright, to find any turning point, first things first, we need to define it, yep? So let that equal to 0, you get x equals minus 1, just like we said. And then, obviously when x is minus 1, this cancels out and you just get a 7. Perfect. Now, because they want to sketch this curve, we're just going to whip out an axis like this, And the key idea, guys, is to firstly plot this turning point. So notice how we got minus 1 and 7. So what I'll do, I'll go minus 1 across and then go up by 7. So I'll put it over here. So in this case, I'm going out in blocks of 2s. Now, because we know what minus 1 and 7 is, we can plot like a little curve like that, and this would be our where the turning point is going to lie. This is the coordinate where it's marked. Now, another thing is, guys, is because they also want us to show like any points of intersection. In this case, your only point of intersection is going to be over here at the y-axis. And we need to remember, when something hits the y-axis, we know that x equals 0. So I would go ahead and use this original equation here, replace x with 0, just like we did here. And again, you can call this y if you like, because that's what fx is. Fx is literally y. And we replace x with 0, just go ahead and smash in the calculator, you're going to get a 9. And that's it, guys. That's part B done. Now, moving on to the next part, which is part C. It says, describe fully the transformation that maps the curve with equation y equals fx onto the curve with equation gx. Alright, so this is kind of a little straight up mapping here, replacing one with the other. So here is our gx function. We're going to come to this one in a second, yeah? Now, looking at gx for a second and then looking at fx, we just got to spot what's going on. Like, they don't actually tell you what's going on, we have to actually see it. Now, it's not very clear what's happening at the end, but in the beginning, you can kind of see how they replace this 2x squared with 2 times x minus 2 all squared. That literally tells us that x has been replaced with x minus 2. Now, the question is, why hasn't this one got x minus 2? Well, that's because they probably already expanded it and then added some kind of constant and got minus 3. Now, to do that, guys, I would literally write this. I'll say, alright, knowing the fact that gx is kind of related to fx, we can say let gx equals the function of x, of the function of f itself, replace every single x with x minus 2, and then add some constant k, because maybe there might be some kind of extra values, we don't know. So let's do it. Let's go to update this function f with x minus 2. That means all the x's look like that now. 2 times x minus 2 squared plus 4 times x minus 2 plus 9, and also the plus k which added. Okay, now what can we do here? Notice on the last bit you got 4x minus 3, yeah? So let's just go ahead and expand the right hand side, yeah? Leave the left hand side alone. So on the right we got 4x minus 8 plus 9 plus k. Tidying up this bit, so minus 8 plus 9 will give us 1. So in the end we have k plus 1. And now matching up terms, you can see that everything looks kind of the same. The only difference is now is that you got minus 3 here and a k plus 1. So I'll go ahead and say, okay, this must mean that k plus 1 has to be minus 3. Take away 1 across, you should get minus 4. And that's it, guys. We essentially have a transformation now. Like if you look in the beginning, it said gx equals f x minus 2 plus k, okay? We know that this function tells us there's a shift. Now because x minus 2 is going to be shift on the right, and plus k means it's going to be up or down shift. Because k is minus 4, it's going to be a downward shift. So in other words, it's going to be translation of 2 across to the right, positive, and 4 down. Or in other words, it's going to look like a vector like that. Okay, so this is your vector transformation. 2 across and 4 down. And yeah, that's CI done. Now for the last bit, for part 2 of that question C, it says find the range of this function. Okay, when it comes to ranges, guys, ranges deals with heights, yeah? Like how far it goes, like the minimum and the maximum, to generalize it. So we need to find either a maximum or a minimum. Now looking back at this function, this is function h. We got 21 over this. This little bottom bit is fx. That means I could go ahead and say that this function equals 21 over fx. Now, because we're dealing with like maximum and minimum, I would use the turning point, because if you remember from the previous question, we had a graph and it told us some kind of, it was a U-shaped graph, and then we had a turning point. This is going to be used here again. So let's go ahead and replace fx with that turning point equation, yeah? Now, this is going to tell us a few things, okay? We know firstly that the turning point was at x equals minus 1. What happens if we replace this minus 1? Let's just check it out. This is what we get, yeah? If x is minus 1, put this in the calculator, this is 0. You just left with 21 over 7. And simplifying that, you get 3. Okay, so this 3 is going to either represent the maximum shape of the curve or the minimum. So this is going to be your highest or lowest value. So how do you know which one's going to be? Well, what I will do is that I'll get a table of values, yeah? And I'll just plug in like a bunch of positive values. Okay, I'll just go ahead and just plug in. And if you plug into the equation, you'll notice that, I don't know, from 0 to 100, it's kind of decreasing here. Like you get 2.33, 1.4, and so on. So far we know the highest is 3, but it seems to be going down towards 0. It doesn't seem to dip below 0. And the reason why Because if you realize, if you plug in any negative value here, just for instance, yeah, and you square it, it'll be positive. That's why if you did another table of negative values, you'll notice that when x is minus 1, again, you get 3, which is the highest it can be. And if you plug in any other value, like between like minus 100 or plus 100, you're just going to get a bunch of positive answers between 0 and 3. And that's it, guys. That's your range. Your range is literally capped between 0 and 3. I don't know how the curve actually looks like, but we don't have to plot that. And if we write the answer, we can say that the range is a function of h between 0 and 3, except that it includes 3 and it doesn't include 0. So, number 6. Solve for theta between minus 180 and plus 180, the equation below, giving your answers where necessary to one decimal place. And there's also a part B too. Now, to deal with a question like this, my advice, guys, is to firstly understand what do we want to achieve here. Yeah? Well, the objective usually, guys, is to either like solve these kind of trig equations in either sines or causes. Yeah. The reason why is because those two are closely related, and they're the easiest to reduce things to. Now, let's have a look. Sine 2 theta is known as a double angle trig identity, and double angle trig identity tells us that this is supposed to equal 2 times the regular sine theta times cos theta. And tan theta is also another identity. Tan theta itself is equal to sine over cos. Okay. Now, what we're going to do, we're going to substitute both of these into the equation, so it's going to look a bit like that. You're going to get 5 times what you just got and 9 times the second identity. And luckily, you know, on the first side, 5 times 2 is 10, and 9 times that is just, well, just stick it together. So you get something like that. Now to tidy this up, my advice for any single question that has fractions is to clear the fraction. So let's multiply cos theta across. So you multiply cos across, you're going to get, what's it called? You're going to get 10 sine theta times cos squared theta, okay? So just stick these together. And then at this case, I mean, I would say minus 9 sine theta across. You could, but we need to firstly try and make all of this in terms of one identity. In this case, we're going to make it in terms of sine. Why? It's because cos squared theta alone is actually another identity. Well, it's actually part of an identity. It's part of the sine squared plus cos squared equals 1. And this identity can be rearranged to make cos squared theta a subject. So you get 1 minus sine squared theta. So let's go ahead and substitute all of this thing into this equation. And if you do that, you get that. 1 minus sine squared theta equals 9 sine theta. So almost done. Almost done. Now at this stage, I'm going to just line this up. At this stage, I'm going to go ahead and expand this, and you're going to get 10 sine theta minus 10 sine cubed theta, because sine theta times sine squared is sine cubed. You also get 9 sine theta. Lastly, we'll now collect like terms. And now, and then if you rearrange this, you can subtract 9 sine theta across with 10 sine theta to get 1 loss of sine theta, and then minus 10 sine cube theta. And guys, be careful with this step here. Whatever you do, don't move this other side, because if you start cancelling terms out, you actually ruin the answer. Instead, we need to factorize sine theta out both of them. And if you do that, you're just gonna get 1 on the left, and you're gonna be left with a 10 sine squared on the right. And that's it, guys. So let's just pull this across to a fresh page, yeah? So from here, what do we do this? Well, it tells us that this times this bracket gives you 0, meaning just like a normal quadratic equation, you have two solutions. Sine theta equals 0, and also the term in the bracket equals 0. Except you can rearrange this and make sine theta the subject. You know, you can, like, I don't know, subtract 1, divide by minus 10, so you get a tenth, and then square root answer. So you get plus minus the square root of 1/10. Okay, great. Now, what can we do from here? So at this stage, the purpose of this question is to find all the solutions of theta, right? So let's go take sine theta equals 0. If we rearrange this to get the sine inverse, well, the sine inverse of 0 is 0 degrees. And yeah, we do the same for the second part. You got sine theta equals plus minus root 1 over 10. Well, let's look at the positive. If we sine inverse the positive solution, you get 18.4. And if you sine inverse the negative solution, you get minus 18.4. Okay. So when you get all three solutions, you know, this is actually not the end of the question, because there's actually a bunch of other solutions that we ain't seen yet. And the reason why we know this is because in the question it said find all solutions between minus 180 and plus 180. So far we've only got a few in the middle. We ain't even got the endpoints. Well, to get endpoints, all we need to do is firstly draw the sine graph, yeah? And if you remember correctly, guys, a sine wave looks like this. So from minus 180 all the way across, you know, this is what we have. the endpoint here is plus 180 and the left endpoint is minus 180 degrees. Okay, now to get all the solutions, this is what I would personally do. I would take this value we just found, which is plus root 1 over 10. And this is kind of a straight line that cuts through the y-axis. So if you draw a straight line of this value here, so just make it somewhere above, it'll look a bit like this. And it'll hit at 2 points. One over here and one over here. Now, if we think about it carefully, guys, we just think about it. We know that the first point here must be 18.4 degrees, yeah? Because that's what we got. And there's another one here. And if you look at it, this is 18.4 degrees away from 0. Because the sine wave is symmetrical about its peak, so in other words, in the middle, it's like literally bang in the center at 90. That means over here is just close to 180. So we've actually got a value which is 18.4 degrees off 180. So we can kind of subtract it. And before we do that, we can kind of do the same for the negative version. So just draw a line across and hit at 2 points, and we get more or less the same result. We know that this very first point close to 0 is minus 18.4, and this is kind of in the same position as it was above here. So this is 180, 18.4 off 180 on the negative scale. So essentially, in your calculator, if you just write 180 take away 18.4, you're going to get a plus minus solution of 161.6. Makes sense. So that's actually your two endpoints. Now, we have to be careful not to forget one other value. That's 0. Because if you look at this 0 here, this means that it crosses the y-axis at the origin. In other words, you're looking at the x-axis. So we can just say that these 3 points is where the curve hits the x-axis. So at these endpoints, we know one of them is 0, and the two endpoints must be plus minus 180 degrees. Okay? And oh yeah, it's good to summarize all your results. So because they want one decimal place, we can write 0.0 and plus minus 18.4. And that's it, guys. That's this part done. Now, let's go ahead and look at part B. So deduce the smallest positive solution of this equation. Okay, so this is not so obvious here, but if you remember from part A, this is the exact same equation as what we're given. The only difference is that this part was 2 theta and this bracket was just theta. So if you think about it, we could say that x minus 25 is actually theta. And this is kind of following on from part A. So we kind of have to use all the angles we had previously to resolve this. Now, when it says find the smallest positive solution, it means find x, yeah? So if we add 25 across, we want to find a solution that says theta plus 25, but the smallest x value you can get. So let's just whip out the previous solutions, yeah? This is what we had earlier. Now, if we think about it, we can't use these massive values. Like, we can't use the positive values because it will be a huge x value. We can't use the negative values because you'll still be negative. 0 is kind of useless for the same reason. Well, not useless, but it can be, right? However, 18.4 isn't so bad. If you plug in plus 18.4, well, you're going to get a big value. But if you plug in minus 18.4 and add 25, you're going to get a value just bigger than 0, which is actually 6.6. And yeah, guys, that's literally all you do for part B. Now, 7. It says in a simple model, the value, be pounds, of a car depends on its age t in years. Alright? The following information is available for car A. Now, it says that its value when the car is new is 20k. And the value after a single year, it means it dropped by 4k, 16k. Now, use an exponential model to form for car A a possible equation linking V with t. Alright, so let's just ignore the other two parts here. Now, what it's trying to say here is that we just need to pull out an exponential model. Well, the exponential model is always the same, yeah? It's always going to be V equals some random constant, like the value of the car, for example, and how much is either exponentially increasing by or decaying by. Well, when we deal with cars in real life, you know the value is always tipping or dropping every single year. The first year is always a massive drop, and then it suddenly like kind of slows down. That's kind of what this equation represents. It's the decaying equation. Now, let's have a look at the bullet points. It said in the beginning that its value when it's new is 20k. So this means at time 0, because remember we're working with time t here. At time 0, like immediately after you got it, the car is 20k. So we have a value of the car equals a equals e times k to the power 0. Remember, so all you do is replace v of 20k, the value, and time, which is how long it's been, with 0. Now, simplifying this equation ain't so bad. We need to recognize that k times 0 is 0. E to the power 0, or anything to the power 0, guys, is 1. So we're just left with a times 1, which is 1. So this means that 20,000 equals a. And that's it, guys. We got our a. Now, the second bullet point tells us that its value after 1 year is 16k. This means car after 1 year, t equals 1. so it's been a single year. So we're going to go ahead and use, in this case, the v equation again, but we're going to update this a value 20k and replace v here with 16k. And of course, t itself is 1. So this is what we got. Now, the purpose of this, guys, is to literally find the value a and k, right? We found a. Let's go ahead and rearrange to find k. So what I will do, I'll go ahead and drop 20k across. So we've got 16k over 20k, which is 4/5. E to the power of that is still ek. Okay. And to find the value k, we need to get rid of the e. And to get rid of the e, we need to take the natural log. So take ln on both sides. If you take ln on the left, well, you leave it like that. If you take ln on the right, well, ln and e cancel out. So then you just get k. And that's it, guys. That's your value k. But they don't tell you how they want it in. So because they don't tell you, you could leave an exact form, or if it helps, I would round up a bit. I would leave it in decimal form. So therefore, k equals negative 0.223. And the reason why this is looking right is because we know that the value car is dropping. And because there's a negative in front, it means it will be dropping. If it was positive, that means the value will actually go up, which is kind of messed up because it only works with antique cars. And yeah, so this should be okay. So putting everything in, replacing your a and your k into the original v equation, you should get a general valuation of a car in this form. And this should cover part A. Now, let's follow that with part B. Yeah? It says that the value of car A is monitored over a 10-year period. Its value after 10 years is 2k. Evaluate the reliability of your model in light of this information. Okay, so they kind of want some kind of description afterwards. Now, first things first, we know that the value after 10 years is 2k. But before we do that, let's go ahead and replace t with 10 and see what happens, yeah? So we can say after 10 years, the value is going to look like that. It'll be 20k times that. Busting this in your calculator, you should get an approximation of 2,150 pounds. Now, the reason why this is reliable is because if you take this to one significant figure, you'll get 2,000. And that's really it. This is why the model is reliable. Yet you have an answer which is approximately similar to whatever system they're following. And that's cool. That's what you need to do. Now, let's look at the final part of this question. It says that the following information is available for car B. So we've got another car with different specs. It has the same value when new as car A, so they both start at 20,000. Its value depreciates more slowly than that of car A. So that means the decaying factor is a bit less, well, closer to 0. Explain how you would adapt the equation found in part A so that it could be used to model the value of car B. Alright, so one marker. So it's literally what we were just saying. We just look at the bullet points. So because we know it has the same value as car A, this means that when a car is new, it has the same value. So for car B, for the coefficient of A, using the original equation, it's also 20k. However, because it depreciates more slowly, we say this. We say that the exponential decaying factor, in other words, the negative power on E, will be less negative or closer to 0. This means that instead of like minus 0.2, it could be like minus 0.1 or minus 0.05, but not at 0, but between those two ranges. So for question 8, we're given some kind of figure, and this is actually a cubic graph. We know it's cubic because it hits the x-axis at 3 points. So one here, one at the origin, and another at this point here. Now, figure 2 shows a sketch of part of the curve of equation y equals x times x plus 2 and x minus 4. And these are the roots of the equation. And the way this works is that if you just set y to 0, you're going to have x equals 0, which is the origin. You got x plus 2, which means that x has to be minus 2. So this is the root here. And because you've got x minus 4, the other root will be x equals plus 4. So you got here 4, 0, and minus 2. Now, let's just move on to the next part. Now, looking at the question, it says that the region R1 shown in figure 2 is bounded by the curve and the negative x-axis. Show that the exact area of R1 is 20 over 3. Okay, so let's just focus on A and ignore parts B and C for a second. Okay, so let's just pull out R1 for a second, yeah? Now, just going back from what we said that the roots of this equation have minus 2 on the left side and 0 on the right. And now to work out the actual area of the shape, we can't use the traditional method. We have to use integration, yeah? And the general form is like that. It says that the area is equal to some integral with some limits, and the limits are basically your x-axis, yeah? It's from where to where. So in this case, L is your lower bound, so we can say it's from minus 2 up to its upper bound, which is 0. And then we need to integrate some equation of y. And our equation of y is here, okay? It's x times x plus 2, x minus 4. Now, to deal with this one, what I would recommend, guys, is I'll just expand this fully, yeah? To get a nice cubic expression. So let's deal with the second two brackets here. To expand the quadratic, we just do term by term. You should get something like that. x times x squared, x times minus 4 is minus 4x, plus 2x minus 8. And then collect the like to the two terms in the middle, because you've got minus 4x and plus 2x. That gives us a negative 2x. And the last step, just times everything by x. And everything should increase by 1 power. So you should get x cubed minus 2x squared and then minus 8x. Alright, great. Now that you've got this equation, we can just substitute this back into the area equation. So replace y with that. And again, replace your limits. So you've got u, which is the upper limit, which is 0, and the lower limit is negative 2. Now, that's our value for R1. So integrating this step by step, and remember to integrate, you just increase the power by 1 and divide it by itself. So it will look a bit like that. You can get x to the 4th over 4, x to the 3 over 3, and then x to the 2 over 2. And then because you've got limits, we put a nice square bracket with 0 and minus 2. So what this means now, we're just going to have to substitute all these values with 0 first, and that's kind of easy. If you replace everything with 0, you're just going to get 0. Now, if you replace everything with negative 2, so copy out of negative 2, you get something like that. And thankfully, this is a calculator exam, guys, so you can just whip this all in the calculator, and you'll definitely get, well, inshallah, you get 20 over 3. And that's it. So that's part A done. So let's just keep this and move on to the next bit. Now, on the second part, it says that the region R2, also shown shaded in figure 2, which is, again over here, is bounded by the curve, the positive x-axis, and the line with equation x equals b. Now, be careful, guys, yeah? They said x equals b, but this does not mean like we have to, it's where the curve intersects the x-axis. Now, this is just a random point b, yeah? Now, it says that b is a positive constant and is somewhere between 0 and 4. We know this root here is 4, so this is going to be less than 4, but bigger than 0. Now, given that the area of R1, which is the first bit, is equal to area of R2, meaning this part is 20 over 3, verify that B satisfies this equation. Alright, this is kind of different to your typical show me, guys, because show me means you have to get to that step. This is kind of tricky because this is, in fact, if you expanded it out, is a quartic equation. Quartic means you literally go to the power 4. So that's kind of a bit something. But let's just think about how to get there. Now, they told us that the area of R2 is equal to area of R1. How about we just use, find the area of this using integration from 0 to b instead? So doing the same thing, using the same expression, we can say integrating from 0 to b of that equation, which we've seen, the cubic one, it should give you 20 over 3. Well, if we had to use the same method, if we integrate this step by step, you get x to the 4th and so on. Basically, you can copy the last one. The only difference now is that you replace all the x's with b and x with 0. Well, we saw last night that when you replace a 0, you get nothing. If you replace a b, you get that. So that's okay. And again, this is all equal to 20 over 3. Yeah, so guys, at this stage, we just want to go ahead and just clear that fraction, yeah? So I'm going to go ahead and just multiply these lot by 4, okay? Because what happens when I do that? If you multiply by 4, well, that cancels out. In your calculator, you can write 2/3 times 4, gives you 8/3. 8 over 2 times 4 is just 16, conveniently. 20/3 times 4 is, well, 8 over 3. And once again, let's multiply this by 3 to clear out the 3's, yeah? So you're going to have the same expressions of 8b cubed and 80, so that stays the same. And you're going to get 3b to the power 4 because you multiply that by 3. Times 16 by 3, you get 48. And that's it, guys. You literally have this. So once again, let's just pull this to a fresh page, yeah? If you remember, we want it to equal 0. So let's just minus 80 now. Now, just thinking about what to do next. We want to somehow factorize this, yeah? But there's a cool method because actually it says verify. It doesn't say show that, meaning you can kind of work backwards. So instead of factorizing this, we can go ahead and expand this previous expression, right? So we can say that, okay, let's verify this by working backwards and expanding above. Because I'm not going to lie, guys, sometimes it's a bit tricky to kind of go from here to there. You can technically, I mean, you could, do long division twice. You'll get that. That's actually a legit method. You can do long division. But let's do it this kind of way, yeah? So let's go ahead and expand this bracket. So let's just pull it out for a second. Now, we know we've got b plus 2 squared, meaning we've got 2 brackets, yeah? So what we could do, I'm going to go ahead and expand these first 2 brackets first, because they're kind of easy to do. If you do that, you get b squared plus 4b plus 4. Okay, cool. Now, I'm going to go ahead and multiply all of this by the second bracket. The nice way to do this is to distribute each of these terms to this bracket. So it look like this. So all we have to do now is just multiply this entire bracket by b squared first, and then 4b, and then finally 4. Okay? So what do we get? Multiplying the first step by b squared, you should get this. Everything goes up by 2 powers of b. Multiplying the next set by 4b, you should get this. And finally, multiplying the last by 4, again, you should get this. And all this is equal to 0. And you're left with this, yeah? So just collecting like terms, minus 20b cubed plus 12b cubed will give us just minus 8, like the one you want. Simplifying this, you should get a final result of that. And that's it, guys. There's literally nothing to it. And yeah, so we've kind of verified it. And when you verified it, just say verified, and you're done. Now, moving on to the final part. So the roots of the equation, 3b squared minus 20b plus 20, and this, by the way, guys, is actually the second bracket from here, the quadratic bit, okay, are 1.225 and 5.442 to 3 decimal places. So these are two roots we get from this quadratic. The value b is therefore 1.225 to 3 decimal places. So I don't know why they can repeat that, but okay. Explain with the aid of a diagram the significance of the root 5.442. Okay, so in other words, what's so special about that second root? So what it's trying to say here, why is this second root so important? I think the better question is, why are they both important? Well, when we evaluated the integral previously from 0 to b, we said that was supposed to equal 20 over 3, okay? So technically, this means that the net total area between 0 and b is 20 over 3. Now, because you got two values of b, you actually have two net values. From like 0 to 1.225, the area is 20 over 3. Also, the value from 0 to 5.442, the net total area is also 20 over 3. So it's just telling you where it is. So we can say, alright, therefore, the quartic equation tells us that the net total area between minus 2, in other words, like, because remember there's also a b plus 2 in the equation, and the other root is 0. But let's look at it visually for a second, yeah? Let's just draw a quartic graph. So let's draw a cubic equation. Now we know what the roots are. The first b root is over here, 1.225. And the second one is going to be kind of on the edge. So let's just say it's over here, just sake of convenience. Remember, this root here is 4, and this root here is minus 2. We've got a bunch of areas here, R1, R2, which we know. We also got R3 and R4, which is new, just for the purpose of the example. We know that the first two areas is 20/3, and because we know that the net total area between 0 and b, so 0 in this point or 0 in that point is 20/3, we can actually say that these two have to be equal. Okay, they have to give you a net total return of 0. So in other words, we can say R3 equals R4. You don't need to work out, guys. So in the end, we can just say, alright, to make this sense of this equation, I think the first point is enough, by the way. But you can also say something like the areas above the x-axis, R1 and R4, must equal areas below the x-axis. So you can kind of see that if you add up these areas and subtract against these areas, you're going to get a net total area of 0, just like we assumed. And that's it, guys. I think this is just one way to explain it. I'm sure there's other ways, but all they kind of really want to say is what happens between 0 and b's. So 0 in here and 0 in that. If you get that far, then you probably got the mark. You can extend it by including the whole graph. But yeah, let me know what you guys got, yeah? We can talk about it in the comment section, because this is kind of, I'll say this is one of the trickiest questions to actually solve, because it's a bit odd, and no one's actually really seen something like this before. But yeah, let's move on then anyway. So, number 9. So given that a is bigger than b, which is also bigger than 0, and that a and b satisfies this logarithmic equation, show that you can get this equation. Okay, so I'm going to skip b for a second. Now, we just got to know some properties of logs here. First things first, when you subtract two separate logs, it's the same as dividing the terms inside. So it looks a bit like that. Log a minus log b is log a over b. And that's going to equal the right hand side. Now, a unique feature of this is that you're trying to get rid of the logs, right? If you've got two equivalent expressions, so this is saying the log of that must equal the log of this. This is implicitly telling you that the inside equal each other. So a over b equals a minus b. Now the rest is simple. To get this, to pretty much solve this, let's clear the fraction, yeah? Let's times b across. If you do that, you get this. Expand the bracket, you get ab minus b squared. Now, to get a, the subject itself, we go isolate it. So what I would do, I would probably subtract ab across, like that. Then I'll factorize it out. And then finally, I'll divide 1 minus b across. And you get something like that. Now, this kind of looks a bit like this one, except it's got a negative sign as 1 minus b. The good thing is, if you just factorize 1 minus b out, times it against the negative sign, this becomes minus 1 and plus b. Or we can rewrite it as plus b minus 1. And that's it, guys. It's shown. Now, for the second part, it says write down the full restriction on the value of b. Explain the reason for this restriction. Okay, so I'm going to pull this out for a second, yeah? Now, previously, let's just go back again. The restriction was that A is bigger than B, which is also bigger than 0. Okay, cool. Now, before we get to that restriction, let's just talk about what do we know about fractions, yeah? We know that when we're dividing things, we can't divide by 0. So essentially, B minus A can't be divided by 0. So we say that. So this essentially means if you add 1 across, B cannot be 1 because it's undefined at 1, meaning it's not possible. Now, going back to the very first restriction with A greater than B greater than 0, this tells us that, if A is greater than B and B is greater than 0, we can just focus on this A part, which is this expression. We know all of this is also greater than 0. A is greater than 0, meaning the whole fraction is also greater than 0. However, guys, it's positive. So greater than 0 means it's positive. We also know that it can't be 1 because 1 is undefined, and it can't be value less than 1. Why? Because if you had like 0.5, this will give you a negative result. That ain't going to work. So we know B itself has to be bigger than 1. And that's literally it, guys. You've pretty much got the restriction. So if we combine it all together, instead of saying A is bigger than B is bigger than 0, it's now going to be A is bigger than B, bigger than 1. And yeah, I think this covers this question. Now, let's go to the next one. Alright, proofs. Oof. So, 10i. Prove that for n in all natural numbers, so n literally means natural numbers. Example of natural number, guys, are like 1, 2, 3, 4, 5, 6. So just ordered numbers. There's some definitions that start with 0, but that's not a big deal, yeah? Now, prove that for all n of natural numbers, n squared plus 2 is not divisible by 4. Okay, now whatever you guys do, don't just plug and play, yeah, because you can't just choose a number and hope it's divisible by 4. You kind of have to rewrite this using an actual equation, yeah? And the way we do this, we need to write an even function, an even equation, and an odd equation. So let's take one. Because we want to divide by 4, we're just going to let n equals something that's 4, like n equals 4m. And we know this is an even number because if you think about 4 times anything is even. I could have just said 2m, or 6m, or 8m. That's the point. As long as it stays even, it's good. Now, because we let n equals 4m, let's substitute this into the equation, yeah? So I'm going to call it a function of fm, replacing this with 4m squared plus 2. If we expand the bracket, guys, we're going to get 16m squared plus 2. Now, if we factorize 4 out of this, so let's just factorize 4 out. Let's just see what happens. You can factorize the first term, but obviously you can't factorize the second because dividing by 4, you get 2 quarters or half. And you can see that alone is not a whole number. So our conclusion for the first statement for even functions is that this function is not divisible by 4 since 2 quarters is not a whole number. And yeah, that's cool. I mean, you'd think this is it. But it says proof for all n. So this is not all n. This is just even numbers. So we also need odd numbers. So let's let n equal an odd number. So you have an even number plus an odd number. So 4n plus 1. So whatever this is always even. Add 1 makes it odd. So this statement holds, yeah? Now repeating the process above here, we're going to have 4m plus 1 squared plus 2. Expanding the squared bracket, you get 16m squared plus 4m plus 1 plus 2, which is basically plus 3, yeah? And then repeating this one, factorizing 4 out. You can do it for the first 2 terms. However, last time you can't because dividing 3 by 4, you get 3 quarters. And then once again, the conclusion is the same. Not divisible by 4 since 3 quarters is not a whole number. And then that's it. Now, to end this always nicely, you always have to say, alright, so for all n, we find that this entire function is not divisible by 4. And that's it, guys. That's a wrap, yeah? That's I done. Now, let's look at the second part, yeah? Second part is slightly, I don't know, I'll say it's easier because you can choose values. It says, given that x belongs to R, now this R stands for real numbers, yeah? Real numbers literally means anything. And by that, you can choose any value. A whole number, a decimal, a fraction. So even pi or exponential terms or logs. Anything is a real number. Anything that is not imaginary, which you can't square it by negative, is real, yeah? So anything that works in your calculator is real. Now, going back again. So given that x belongs to real numbers, the value of the modulus of this, meaning it's always positive, so whatever x value you choose, if you get a negative result, it forces it to be positive, is greater than or equal to the value x minus 9. State, given a reason, if the above statement is always true, sometimes true, or never true. Okay, this was interesting because just looking at it for a second, yeah, it's claiming that this is always greater, or this is greater than that. That's the claim. If you think about it, I mean, if you just choose any value for x, if you choose any negative value, like let's say, I don't know, like minus, let's just say 0 for a second, you get minus 28. But because you got the absolute signs, minus 28 becomes a plus 28. If you put 0 here, you get negative 9. So that's obviously greater. This is true for everything, but there's a trick here, yeah? And the trick is like, is to test some values x and make a table. I'm gonna show you my table right now. That's what I personally recommend do something like that, yeah? I write a table which has x, the first function, and the second function. I'll just plug in a value like 0, like we did. Here you get plus 28, second you get minus 9. Obviously it's bigger. Now what I would also do is I'll set both of these functions to 0 to see like when is it 0. For example, if I set the second equation to 0, you can see that x has to be 9 to make it 0. So if you plug in 9, you would realize that on the first function you get a 1, and the second one you get a 0. And for the second function, if I plug in a 0, I'm going to ignore the negative roots here. I plug in a 0, you get 3x minus 28 equals 0. Solve it, you get 28 over 3. Now, if you plug into the first one itself, obviously you get 0 because that's what we did. If you plug into the second case, you actually get a third. And this is the only, this is one of the few only times that it's actually bigger. The rest of the times the first function is always bigger. And I just test another random number like 9.5. This makes it equal. Again, this was just luck. So you don't like to actually show something is equal. By the way, you just make both these functions equal each other and solve for x, which will give you 9.5. And that's it, guys. And then when you do that, you make a conclusion. You say, all right, it's sometimes true since x minus 9 is greater than this when x equals 28 over 3. All right, number 11. So a competitor is running a 20-kilometer race. Now she runs each of the first 4 kilometers at a steady pace of 6 minutes per kilometer. Okay, so let's just note that down, yeah? First 4 kilometers, this means 24 minutes because 4 times 6 is 24 minutes. After the first 4 kilometers, she begins to slow down. Now, in order to estimate her finishing time, the time that she will take to complete each subsequent kilometer is modeled to be 5% greater. Okay, I'm going to note that down, yeah? Than the time she took to complete the previous kilometer. Okay, so what this means now is that we're no longer doing this arithmetically. We're doing this geometrically. Okay, so it's going to be increasing by some rate. Now, for example, we know that it took 6 minutes to do a race. That means on the 5th kilometer, it will be 6 times 1.05. So it's going to increase by 5%. Likewise, the next one is going to be 5% greater than that. So the 6th kilometer will be 6 times 1.05 squared. And the next one is cubed, power 4, and so on. Okay? Now, using the model, show that her time to run the first 6 kilometers is estimated to be 36 minutes and 55 seconds. Alright, so let's just pull this out for a second. Yeah? Let's just pull it out and take our data with us. Now, we saw earlier that the first 4 is 24 minutes. The 5th is that many minutes, and the 6th is 6 times 1.05 squared minutes. Okay. The total of this. So if you just put 24 and all this in your calculator, you should get a total time of 36.915 minutes. We got the 36 minutes part right. Now for the seconds, we need to convert this decimal into seconds. Yeah. Because think about it, this is 0.9 of a minute, so it's still less than a minute. Now to convert something into seconds, you take that decimal part 0.915 times against 60. And you should get a result of 54.9 seconds. Okay, so this gives you a second result. So we can just round up to 55. So we can say, therefore, the first 6 kilometers run was 36 minutes and 55 seconds. And just add the word shown to show that, you've done it. Now, let's just move on to part B. Yeah? So show that her estimated time in minutes to run the half kilometer. So this is kind of like the nth term for all values between 5 and 20. So this is from the 5th to the 20th kilometer because the first 4 kilometers are just, the arithmetic. You just add 6. It's given by this kind of formula. Okay, so to show this is the kind of formula we need, you can kind of notice one thing. Like if you plug in, like little trick here, if you plug in 5 for R, you get 6 times 1.05 to the power of 5 to the 4, which is 1. So that's referencing the 5th kilometer. For the 6th, if you plug in 6, you get that. So we can kind of make this easy. We just plug in, we just say the 5th is that, like we just said. The 6th is this, meaning if we had to generalize it, if we did it for the half term, it's going to be the same thing but with R. And to make it look like that, just rewrite in what they want. And again, write shown. And that's it. Estimate the total time in minutes and seconds that she will take to complete the race. Okay, so this is kind of chilled. You just need to find the total time. And we know that it took her 20 kilometers, yeah, because that's what it said in the beginning question. And we know the first 4 kilometers was 24 minutes, and then the rest is given by this kind of equation, yeah? You just got to sum them up. So we say, all right, therefore, the total time is going to be the first 24 minutes plus the next 2 terms, 5th and 6th, plus ... all the way to the last part. Now, if you think about it, if you plug in 20 for this one, we know altogether you're going to get power 16. So this means she's going to do this 16 times, yeah? it's geometrically increasing 16 times. Now that's what we need to work out. So I'm going to just like bold it there for a second and make a fresh page. And to resolve this bit, you could just use the sum of a geometric progression formula, so the SN formula. Now the SN looks like this. For geometric series, we got Sn equals a times 1 minus r to the power n, where r is your common ratio, n is the number of terms, over 1 minus r. Now we need to pick carefully what is our a, r, and n. Okay? I think for our a, and a is always the first term, we're talking about the first term of this series. We can see that the first term is the very first thing, 6 times 1.05. Now be careful guys, it's tempting to write 6, but that is not your first term. Your first term is the very first thing that started the geometric, which was that. Our r is quite obvious, it's increasing by powers of 1.05. So that's it, 1.05. And n is the number of terms there are. Well, this is your first term, second term, you got 16 terms, so that's your n. Now all you do is plug this into your formula, and you'll get something like that. 6.3 times all of that, and this is straight up calculation. Drop this in your calculator, you get an S16 of 149 point something. Now, our total time, therefore, is going to be this quantity plus 24, which will give us 173 minutes. Point some few seconds. Now, once again, just like the previous question, we need to somehow convert this decimal bit into seconds, yeah? Now, if you recall, it's just like you take out the 0, so it'll be 0.042 blah, 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 and you times that by 60. If you do that, like this part times 60, you're going to get the second equivalent. So therefore, we say our total time is going to be 173 minutes and 3 seconds. Now, they give you a function which is 10e to the minus 0.25x, and you times that against sine x. Now, show that the x coordinate of the turning points, so when they say turning points, they mean differentiate that, of the curve with equation, what we're given, satisfies this equation. In other words, you've got to differentiate this and somehow rearrange it to get this kind of equation. Now, because we've got two things multiplied, so let's say we've got this term multiply that term, we have to use the product rule, yeah? And this is what we want. We want f prime x to equal 0, or the derivative to equal 0. Because that's how you find turning points. Now, to use the product rule, we need to firstly let something be u and something be v. So I want to go ahead and let the first term be u and the second term be v. Now, the product rule formula looks like this, yeah? So now we can say, okay, let u equal the first term and let v equal the second bit. Now, if we differentiate the first part, and when you have an exponential, all you got to do is just look at its power and just drop it down, yeah? So it'll be 10 times minus 0.25. That's going to give us minus 2.5. And then we always copy the rest. So this part here never changes, yeah? For v, when you differentiate sine, you just get cos x. And if it was the other way around, if you had cos x, it would become negative sine. So that's how it works. They just flip around each other. Now, because you got everything you need, yeah, you got v times u prime plus u times v prime. All you got to do is just pick v and multiply against u prime first to get the first bit, and then, you know, pick u and then times against v prime, and then put a plus between them, just like I did over here. And because, you know, you're trying to find the turning points, you got to let this equal 0. So when you let it equal 0, you can now move, I don't know, 2.5, like this first term across, or however you like. But either way, it should look a bit like that, yeah? Okay. Now, one thing we have to note is that we need to get a tan x, yeah? So let's go ahead and just move cos x across by dividing it and then divide this term across. If you do it, you'll get something like that, yeah? Now, the good thing is, you got the exact same term you're dividing here. So we can go ahead and just cancel these part out right now, yeah? No problem. And in our calculator, we can write 10 over 2.5. That gives us a 4. So that's cool as well. And finally, guys, one final thing to note here is that we want to change sin x over cos x into tan x. Thankfully, that's an identity. These two directly equals tan x. And that's it, guys. We got our answer. And when you get your answer, it's probably better to write the word shown. You know, you never know. I think it's always good to write that. Now, to the next part, yeah? So, figure 3 shows a sketch of part of the curve with equation y equals fx. So, this is what we had previously. So, this is kind of reflecting the first part. This equation right here, yeah? Now, have a look again. B. Sketch the graph of h against t, where this function equals the same function we had here. So if you look back, it's the same function, but now they put this kind of absolute sign. So what I mean, guys, here is that if this original function was fx, so let's just call this function fx, yeah? We now have the same thing, but now they got modulus signs. So what this means, guys, is that when they put these absolute modulus signs, like this means whatever values you had that was negative, it will bounce back to be positive. So you see these values that go below the line, like here, they're currently negative. If you put the absolute sign, instead of dipping below the line, it bounces. So it looks a bit like that. It'll bounce and then carry on, bounce, and carry on. And I think that's what they want. That's all you got to do. You got to sketch that, showing the long-term behavior. Long-term behavior just means, just keep going to the end, and you're done. Now, let's move on to the part C and D, yeah? So, function ht is used to model the height in meters of a ball above the ground t seconds after it has been kicked. Okay, so literally how high the ball goes, yeah? Using this model, find the maximum height of the ball above the ground between the first and second bounce. Okay, to find the maximum or minimum of any single thing, you always got to use differentiation, yeah? Now, if you look back at part A, yeah, we had this, right? We had tan x equals 4. Now, I'm just going to write tan t, yeah? The reason why is because, we're working with t. I mean, you could write tan x, but it doesn't make a difference. Let's just say, call this tan t. Now, to find the maximum height, let's go ahead and just inverse this to find what t actually is, yeah? So if you tan inverse 4, you're going to get something like this. And so one of the features of tan is that it always shifts 180 degrees. So if you start here, wherever this value is, you know that if you add pi, you're going to get right here again. If you add another pi or 180, you're going to get here again. So what I'm trying to say is, all we need to do, like to find the rest of the solutions, is keep adding pi. Okay, so add as many pi's as you want until it becomes positive. If you add pi to minus 1.326 in your calculator, you should get a time of 1.816 radians. In this case, 1.81 seconds, because that's how we're thinking it. We're thinking of it as if it's in seconds. Now, you're pretty much done, guys, yeah? All you go do now is just substitute this value t into this function here. So let's just write in, replace the t with what you need, and then you get a maximum height of 3.18 meters. And that's it. Now for part D, it says, explain why this model should not be used to predict the time of each bounce. So we say here, why this cannot be used is because the time between each bounce changes. And that's it. I think this is alright. So the curve C with equation this, where P and Q are constants, passes through this point and has two vertical asymptotes. Okay, so asymptotes means is that it never ever touches one of the axes, yeah? So it will never reach a certain point. It will just go on forever. With equations x equals 2 and x equals minus 3. Now, explain why you can deduce that q equals 4. Alright, so when they talk like this, all they're trying to say is that we need to firstly look at the bottom, yeah? We're trying to talk about the roots of this equation. That's the thing. So, this is our first thing. We can say this. We can say that the vertical asymptotes, what they're talking about, refers to these two brackets, yeah? And that's when they equal 0. Because the only time you can find a root, or like a solution, if you want, is when they equal 0. So from the first case, let's just look at x plus 3, yeah? We can say that, okay, from x plus 3 equals 0, we can find x equals minus 3. And that makes sense. That's actually one of the roots. Now, the second case is when you find x equals 2, right? And that has to be from this bracket. We can say also, x equals 2 is found from the second bracket, when it equals 0. Now, if you think about, and let's do some writing here. If you replace this x with a 2, so you get 2 times 2, which is 4. You got 4 minus q equals 0. So essentially, we can see why it's 4 now. So we can say, therefore, 4 minus q, when it equals 0, will give us what we want. And that's it. That's not much to it. Now for the second bit, it says show that p equals 15. Now this is cool because the reason why they give us a pair of coordinates, and all you can do, guys, is literally substitute these coordinates into this equation. So replace your x's with 3 and your y with a half, and of course replace like wherever you already have. So q equals 4. And if you do that, you're going to get a massive equation like that. Okay, I like to use brackets personally, like to replace numbers, letters to numbers, because that way you won't make a mistake in your calculator. So if we quickly evaluate this, guys, yeah, we've got 3 times 3, which is 9, so I'll just put this as 9. And then this entire bottom fraction, like you can just put this in your calculator actually, this entire bottom fraction, you should get 12. So that's cool. And now finally, to find p, we just got to clear the fraction. So I would multiply 12 across to get 12 over 2, and oh yeah, and then add 9, and then you're given this. And if you put this in a calculator, well, you can say 12 over 2 is 6, and therefore 6 plus 9 is 15. Yeah, pretty good, isn't it? This question so far isn't so bad. Now, next bit, because there's still a few parts here. Oh yeah, I've updated the function, just to let you know. So because we said p was 15, I replaced p here with 15, and I update q here with 4. So that's why it looks like this. And I just wrote it here for convenience. So for the next part, it says figure 4 shows a sketch of part of a curve C. Now the region R, so this area here, shaded in figure 4, is bounded by the curve C. the x-axis and the line of equation 3. Okay, cool. So here's your line of equation 3, your x-axis, and it cuts at some limit here. So let's just call this one like a u or something, like some upper limit. Okay. Show that the exact value of the area of R is a ln 2 and b ln 3, where a and b are rational constants to be found. Okay, so rational constants probably means fractions or stuff like that, not necessarily whole numbers. Now, just a quick reminder, we call this upper limit u here, because, yeah, sometimes it doesn't go through. Now, let's do it. So to find the exact area, we're always going to use that integral equation, yeah? Which is always what? The integral from a lower limit and upper limit. In this case, the lower limit would be 3, and the upper limit we're trying to find. And then we just use the equation we have. So instead of y, it'll be this whole thing in there. So in order to find the value of u, we can see that this curve crosses the x-axis at that point, yeah? So what we can say is, okay, let's use the curve equation and make it equal to 0. Because when you cross the x-axis, we know the y coordinate is at 0. So we can say let y equal 0. So replace that part with 0. And now to find x, well, we should always try and clear the fraction, yeah? The good thing is, if we multiply all of this thing across, so 2x minus 4 and x plus 3 across, you can have 0 times that. Well, 0 times anything is 0, so you just left with that. And this is easy. You just move 3x across, divided by 3, and you're going to get a 5. Perfect. So updating what we got, we have this. So we can say that the region is going to equal this integral. Yeah. And to do it nicely, I think the best thing we should do is try and factorize some numbers, yeah? So it always helps to break it down. So you see the 15 minus 3x? Let's just put it here for a second. We can actually factorize the 3 out of this. So we're going to have something like 3 times 5 minus x, yeah? And on the bottom half, well, we got 2x minus 4. If you factorize 2x minus 4, so let's write 2x minus 4, you can take a 2 out. So it's going to be 2 bracket x minus 2. And the point of this, guys, is you want to take out 3 and 2 outside integral. And trust me, guys, this will make the final answer easier. So it'll look a bit like that. 3 and 2 is outside this. Now, the next step is to literally separate this into 2 separate fractions, yeah? Because that's the only way to integrate it. When you've got loads of parts like this, like 2 linear terms, you got to use partial fractions, yeah? And for the sake of simplicity, guys, I'm going to stick this 3 over 2 next to the top line, yeah? Because it's the same thing. And the partial fraction says this. You can split this whole thing into one part over x minus 2 and another part b over x plus 3. So now, guys, all we want to do is work out a and b. So let's do it. So what we do next in partial fractions is that we should always clear the fraction, yeah? So we're going to go ahead and multiply x minus 2, x plus 3 across this equation. And when you do that, guys, you're going to notice that these two cancel out and a and b both get the opposite terms. Okay, a bit like that. And now the next step is to actually work out a and b. Okay, and that's what we got to do. Now to work out a or b, all we got to do is just pick 2 values of x, yeah? I'm going to make it easy. I'm going to try and pick a value x which makes this entire term cancel out. And that is 2. So if you said, alright, let x equals 2, you're actually going to get this for the whole equation. You're going to get all this replaced by 2, so you can get 3 over 2 times 5 minus 2, a times 2 plus 3, and then b times 2 minus 2. Well, clearly this part is going to be 0, yeah? Because that's what we want to do. So you're going to have basically 2 parts here. The left side is 9 over 2, and the right side is 5a. And then dividing 5 across, you get 9 over 10. And that's one solution. Now for the next part, we're going to do x equals, we want to eliminate a, yeah? So we can pick another value. Let's pick, I don't know, x equals minus 3, because that cancels out. And if you do that, well, plug in minus 3 across, you get something like that. And you'll notice again, just like the first case, this reduces to 0, because I think that's what we want to do. And on the left side and the right side, they reduce to something like that. That's just 12, that's just minus 5. And again, dividing minus 5 across, and you get a b value of this. And that's it, guys. So you got 2 values. And now what we can do, we can update our integral, yeah? So let's remember, we can just replace our a and b, so we're going to actually use this 2 here, yeah? So always remember, we're using this from now on, yeah? Replacing a and b, what we got. So here's our original integral. It now equals that. Perfect, yeah? So now we can actually integrate both of these. So the rule to integrate this is that when you integrate, you just get a log. That's it. When you get a fraction, you get a log. So naturally, you're going to get 9 over 10 ln that plus, or in this case, minus 12 fifths ln x plus 3. And we've got limits here, so we're going to integrate from 3 to 5. In other words, you're going to firstly plug in 5 for x, wherever that is, take away, plug in 3. We're going to keep this in exact form, because the question said, give your answer in the ln form, yeah? So replacing x with 5 first, you're going to have 5 take away 2, which is 3. 5 plus 3, which is 8, so that checks out. And then minus, and I use a curly bracket. You can use a circle, like the regular curve brackets. And then replacing x with 3, you get ln 1, and you're going to get ln 6. That's it. So let's take this on the first page again. Now, the nice thing about this property, guys, yeah, is that this entire part ln1, well, ln1 is actually 0 in your calculator. This will give you a 0. Okay, so that actually crosses out. So what you're going to actually have now is just this, yeah? It simplifies nicely. So what we could do is just expand the bracket. You got double minus, makes it a plus. And yeah, we're almost there. If you remember correctly, guys, yeah, the question said that we need to find the exact area of this in terms of ln2 and ln3. Well, so far, this part is cool, yeah? We got that. However, these two are not in the right form. Now, we kind of have to change the right form. The good thing is, guys, yeah, we can use the calculator to check out ln8, which simplifies, but the calculator does not simplify ln6 properly. So what do? We take each of them, yeah? So let's take the first one, so I did over here. So the good thing is you can just write ln8 in your calculator and you're going to actually get 3 ln2, which is nice. And then, well, 12 fifths times 3 is just 36 fifths. So you're going to have minus 36 over 5. And that's cool. That's literally one of them done. So you got another term ln2. Now let's take out ln6 here. Let's focus on this one for a second. Now, you can't do the same trick because I've tried it and you still get ln6. What you have to do instead is to realize that there's some kind of rule here. Now, if you remember, if we like multiply two ln's here, so let's say, I don't know, sorry, if you add up two ln's, like ln a plus ln b, we actually get ln a times b. Now, we have to kind of work backwards, yeah? So we can kind of see that ln6 is the same as saying 2 times 3, or in this case, ln2 plus ln3, okay? And well, if we expand the bracket, you're going to have 12 fifths distributed to both of them. So that's how it looks. So therefore, guys, we can now substitute both these expressions for the first two. So for this one and this one, and now writing it below here, yeah, we should get this. That's it. And all you do is collect like terms, yeah? So in our calculator, I don't know, we can say 9 over 10 plus 12 fifths and minus 36 over 5 and 12 fifths. So do them separately, you should get two terms. Minus 24 over 5 for ln2 plus 33 over 10 for ln3. And that's it, guys. We've done the question. In the mark scheme, however, they'll give you a decimal form. So they'll write this as 3.3 and minus 4.8. So both is fine, guys. Both is fine. So we have a curve C in a standard Cartesian plane and is defined by the following equation. Okay, so notice that now x is the subject. It's usually y, yeah? So we need to be careful with that. It says that the curve C passes through the origin. So we know it passes through the point 0, 0. Find the value of dy over dx at the origin. Okay, so this is dy over dx. We can't do dy dx. We can only do dx over dy. Yeah, so that's what we want to do. Now, to differentiate this one, it's just the same rules. You literally differentiate sine. We know sine becomes cos. And because you got 2y, it will become, instead of 4 sine 2y, it becomes 8 cos 2y. So you always differentiate 2 and you multiply against the 4. 4 times 2 is 8. And now it says find the value of this at the origin. So you just replace y with 0, and you're going to get something like that. You say at the origin, we have this. Cos 0 is 1, so 8 times 1 is 8. Therefore, that's dx over dy. Therefore, dy over dx is the reciprocal, is 1 over. So it'll be 1 over 8. And you got it, guys. This is literally all you got to do. Now, for part B, it says use the small angle approximation for sine 2y to find an equation linking x and y for points close to the origin. Okay, let's be clear, yeah? For the small angle approximation, when you're dealing with sine, so let's say sine theta for a second, yeah? This is approximately equal to itself, theta, for very small values of x. For small values of theta, sorry. What that means is that theta has to be like, I don't know, 0, 0.1. So basically close to 0, very close to 0. It can't be 1. Sine 1 doesn't equal 1. Sine 1 equals something else. Okay? Now, for part 2, it says explain the relationship between... Oh, wait, we haven't done it yet. Use a small angle approximation for sine 2y to find an equation linking x and y. Okay, so let's do the same thing. If sine theta is approximately theta, that means sine 2y is approximately 2y. So we can actually replace this sine 2y with 2y from the beginning. So we're going to say, okay, that means x is approximately 4 times 2y. So therefore, we can say that x is approximately 8y. And part 2, explain the relationship between the answers to A and BI. Okay, so let's just have a look a second. For part A, we have basically got a gradient dy of dx of 1 over 8. Now if you look at this equation, this is actually the same thing. If you make y the subject, so let's divide a across, you're going to have y, which is approximately 1 over 8. So in fact, all it is that they both have a gradient of 1 over 8, and that's your answer. So you can say the value of 1 over 8 is the gradient in both parts. That's it. That's, I think, all you should say. And now let's move on to the final part of the question, which is part C. So let's do this, and then we can wrap up. So show that for all points in the x and y coordinate lying on C, we can get this gradient equation, dy of dx, where a and b are constants to be found. Now, the problem with this question, guys, is that there is no actual build-up to this. Yeah, we don't really know where we're going. But in fact, we have some information, you know. We're given an x value of this from the previous question, and we found out that dx of dy was this. Now, but they want dy over dx, not dx over dy. So immediately, we need to flip this upside down. So it's going to be 1 over a cos 2y, which equals dy of dx. So the next step now is how do we go from cos 2y into this square root function, okay? And there's a nice trick to that. The trick is that we need to use an identity, a trig identity. You can't use the sine x over cos x equals tan identity. So we're going to use the other one, which is the sine squared plus cos squared equals 1. Because our angle is basically 2y's, we're going to replace that usual x or theta with 2y. So this is our identity. So what we can do, we can go ahead and make sine 2y the subject for the first x equation. So if I divide 4 across, we're going to have x over 4 equals sine 2y. Okay, and I'm going to go ahead and substitute this x over 4 into the sine squared expression. So it's going to be x over 4 squared, meaning we're going to have x squared over 16 plus the rest, and copy the rest. Now, what we want to do, we want to try and make cos 2y a subject so we can factorize into here, and it will look a bit like that. So minusing this term across and square rooting, you're going to get something like that. So now we can actually substitute this expression into the dy dx, so replace cos 2y with that, and it'll look like this. So it'll be 1 over 8 times that. Now, to solve this completely, we have to try and rationalize this, yeah? So we need to kind of get rid of that 16 and just leave it as a nice x squared, and we're done. And the best way to do this, guys, is to times up and down by root 16. So always times it by itself. That's usually the trick, because it's like times it by 1. So for the rest of this, I'll do it manually. Now, if I times the top by root 16, well, we're just going to get root 16 on the top line. On the bottom, however, we can choose to times root 16 by its surd or by the whole number. Well, because we're working in surds, I like to times root 16 with its actual surd. So you times everything inside by 16. So 1 times 16 inside the surd, well, let's write 8 for a second. We're going to have 16 minus, and then x squared over 16 times 16, well, they cancel out. So you're just left with x squared. Cool, and that's cool. Now, and then finally, guys, well, we know that root 16 is actually the same as 4. So essentially, 4 over 8 is 1 over 2. So our final answer is going to be 1 over 2 times the square root of 16 minus x squared. And that's it, guys. That's this question done. I just want to thank you guys for coming to this end of my channel, and if you've enjoyed the content so far, just go into my channel page, hit the subscribe button and hit the bell for more notifications, and if you want, you can do personalized or all, and that way you won't miss any future maths or educational videos. Anyway guys, thank you for watching and see you next time. Ciao.